Hello and welcome to the final physical science recording for this year. We've got a little bit of math work to do today, just some arithmetic that relates to the periodic table and the elements on it. And so we're going to dive right into that with a little bit of a review, and then we'll see how that relates to the slightly more complicated stuff that I want to show you today. So I'm going to pop over to my iPad. And we're going to start looking at what's called weighted averages, but we're just going to do a quick review of the averages to begin with. So let's say that you have baskets. You have 4 baskets that hold oranges. And in those baskets, you have 12, 15, 23, and 11 oranges. Question is, what's the average number of oranges in each basket? Well, you know how to do this. You know that to find an average, which I'll abbreviate as AVG for here, you add them up, 12 plus 15 plus 23 plus 11, and then you divide by the total number of things that go into it. So 4 in this case, divided by 4. So I would add the stuff up on top first. It's 50, 61 divided by 4. And then when I divide that out, I get 15.25 oranges per basket. Pretty simple stuff for that. That part's not too bad. But of course, averages are pretty useful, and we use them in a lot more complicated situations than 4 baskets with different number of oranges. So let's take a little bit larger sampling. Let's say that you have 3 baskets that each hold 12 oranges, 5 baskets that hold 15 oranges, 7 baskets holding 23 oranges, and 6 baskets holding 11. Now you could write this out, and you could say that, well, the average is going to be, let's see, 12 plus 12 plus 12. That's 3 12s. Then we have 5 15s. And so you would just keep going like this, bleh, too much. The easier way to do it would be to say, well, I have 3 baskets that each hold 12. I have 5 baskets that each hold 15. I have 7 baskets that each hold 23. And I have 6 baskets that each hold 11 oranges. And so that would be, what, 36 plus 75 plus 161. Better check that one. Plus 66 for a total . This is my cat, Mary. No, this is my cat, Pippin. No, I was right the first time. It's Mary. We have 2 orange ones, and I was looking at him from the side. He is inquisitive and doesn't know boundaries. Sounds like, yeah, my daughter says, sounds like every other cat. So that gives us a total of 338 oranges spread out around these baskets. Now we had, over here, we had 12 baskets. Nope, 3 baskets in the first one. We had 5 baskets. We had 7 baskets, and we had 6 baskets. So if I add all of those up, I get 21 baskets. So to find the average, I take my 338 divided by 21 baskets. Okay. And I'd find out that I have an average of 16.095, so basically 16.1 oranges per basket again. That really streamlined it to multiply these numbers rather than add them all up and then take the total. This is kind of, it's close to one form of what we call a weighted average, which means you're going to multiply how many of each thing you have, how many of each variety. So we multiplied the number that we had here, number that we had here, number that we had here, number that we had here. But more commonly, a weighted average will actually say what percentage of each did we have, so that you could represent any large number of things. So this is representative of that. So let's just say we just got a bunch of baskets. Doesn't really matter exactly how many, but we do know that 30% of them hold 12 oranges. We know 15% hold 15 oranges. We know 25% hold 23 oranges, and the remaining 30% hold 11 oranges. Now for this to work, we need this to add up to 100%. That's how a weighted average expresses things. So out of the total, this is a percentage. And then in order to find the average, we're going to treat it very much like the previous question, except each of these are weights. So the weight of this is our percentage. So instead of saying this, now when we want to find the weighted average, I'm just going to put average again, we have to convert this percent into a decimal. Not hard, divide by 100. So you move the decimal place over twice, right? So this would be 0.3 times 12. And then we'd add to that, move it over twice, 0.15 times 15 plus 0.25 times 23 plus 0.3 times 11. And this is just going to plop our average out because we are taking it out of the whole. And if we add up 0.3, 0.15, so that's 0.45, add another 0.25, that gets us to 0.7, and add 0.3, that adds up to 1. That's how we can work this out in one fewer steps. So now I'm going to multiply those together. So I take my 0.3 times 12 plus 0.15 times 15 plus 0.25 times 23 plus 0.3 times 11, and then I just hit equals. So I can use a parentheses if I want. I don't really need to, because a calculator will interpret these multiplications as multiplying and dividing goes before addition and subtraction. So it's going to automatically do those first for us, and then it will come back and do the addition between those terms. And so I end up with 14.9 for my average this time. Notice I didn't really expect them to be the same averages all the way around. I'm just putting in varying amounts. So it's okay that they're different averages. Doesn't mean that any of these steps were wrong. This, though, is a weighted average. And you have seen these kinds of things before, probably in math, of course, but also even in regular in other classes, because it's a weighted average that allows us to calculate your semester grades. This semester, of course, is a little different. We're just taking Q3 and we're taking Q4 and we're averaging the two. Generally speaking, though, that is also averaged with the semester final exam, and those are all weighted. So if we go into, so our fourth example here is that we normally weight the semester grades. First and second quarters are each 45%. And then the total, or the final exam, is 10%. So let's take this scenario where Q1 grade was 75%, Q2 was 83%, final exam was 55%. Final exams, you guys don't study enough, just saying. And we'll see how this goes together into one final grade. So this will be labeled in the gradebook as a FL, final letter grade, even though we're calculating a percentage here. So we take our, how much was 75%? We take this over as a decimal, so 0.45 times 75%. We have 0.45 times Q2, so we're going to add that in. And then we have our 10%, which is 0.1 times our final letter grade, or final exam grade of 55%. And we can, again, just put those in, 0.45 times 75% plus 0.45 times 83% plus 0.1 times 55%. We get a 76.6%. And you might be looking at this and saying, yeah, but we got more percents. Why didn't we divide those out as well? And you can. The reason I didn't was because we were wanted to measure. This is sort of our oranges, right? Orange, orange, orange from our examples above. They were the things that we were counting up, the end percentages. And then this part, let's do a red. These two were how much of it, the abundance of it. And so the abundance part is the thing that we have to make sure adds up to 1. So if we take 0.45 plus 0.45 plus 0.1, we equal to 1. These other things, the 75%, 83, those don't typically add up to 1. So that's how we can tell. We look at the part that we have to translate is the abundance. Now let's see how this works with the periodic table. The other day, we looked at this fancified periodic table that included the relative abundances of each of them in pie graph form. And then it also included some measurements. So we had, for example, boron here. We had 2 varieties, 2 isotopes of boron. And the natural average of those, if you got a whole sample, would be somewhere in that range. That's sort of an upper and a lower bound of the range, depending on exactly what the mix is. But that's, if you just got a random sample of boron, that's what it would be. That is a weighted average, but very often, periodic tables will report them more like our standard one here, where it's just a single number. So if we look at boron again, it was 10.81. That's going to be an average of those somewhere in between. And this is averaging the amount of same thing, right? It's going to be right in that area. This is averaging the weighted amount of boron that is boron 10 and the boron 11, the 2 isotopes that occur in differing amounts depending on the relative stability. And this pie chart tells us the combination. So it looks like a little less than a quarter, so about 20% of boron has a mass of 10 because it has 5 protons and 5 neutrons. And the remaining 80% or so has a mass of 11 because it has 5 protons, of course, and 6 neutrons. And when you take the weighted average of that with a whole sample, remember, you're going to have uncountably many boron atoms. You will get the weighted average that is right in the range of 10.806 to 10.821. Our other periodic table called it 10.81, just to meet somewhere in the middle. Okay, so we're going to do one. Let's do one of those. So we're not doing oranges now. We're going to look at copper. Copper comes in 2 natural isotopes, copper 63 and copper 65. All of them will have the same number of protons. I'm going to pop over to check. I bring up my periodic table. Copper's right here. It has 29 protons. And now, so every copper has that, but now some of them have 34 neutrons here. That's one common isotope, and the other has 36 neutrons in it. And so it's important to know for some circumstances what the average would be. And these occur naturally, that the copper 63 is 69.17% of a natural sample, and the copper 65 is 30.83% of a natural sample. So what I want you to do is figure out what's the average atomic mass. This would be a really good place to just pause, see if you can work it out before I do. And then because the final homework here on this topic includes some of these, but I am going to launch into it right away. So the average mass is going to be 69.17% of it is copper 63. So it's going to be, move that over, 0.6917. And then we want to find the mass. Well, the mass of that sample, of those particular ones, is 63. And then the other ones, the 30.83%, have a mass of 65. That's what those end numbers mean. So we're going to add in 0.3083 times 65, and we'll be able to find the atomic mass of that. Averaging those, a weighted average, I get 63.6166. And for all of the homework questions, I've asked you just to round to the nearest hundredths place. So we'd look at the next one, the 6, that would round it up. So we'd say it's 63.62. The units here, we're not going to delve into the units. The units are called AMU, which is atomic mass unit. Schoology won't be expecting it, so don't put them in. And really, that's just a measurement based on how many neutrons and protons there are. So 63.62 based in this. And that's because it'll be closer to our 63 because there's a lot more of it. There's over 2/3 of it is that 63. So we would expect it to be much closer to the 63.62. Let's compare this to our periodic table amount. Copper, I said, was 63.62. So this is a little different. You might be thinking, what gives? Well, first thing is we are practicing just how to calculate the weighted averages. So we don't worry too much about it. Second thing is, although we say every proton has a mass of 1 and every neutron has a mass of 2, the physics of this is way more complicated, and that is not actually true. There's a slight variation just depending on how they combine. So that accounts for our difference. This is still the answer you'd put for our calculation. Notice it's very close, and it will give you a good idea of what the weighted average is in there. Okay, and that concludes our final video lesson for this semester. Work hard, finish up your stuff this week. I'll still be at work tomorrow or next week, so you can continue to get stuff done. I want everyone to have a successful finish to this. Not everyone will, but I think most of you can and should. And so work hard. I'll be there to support you.